This lecture will be about some of the more fun aspects of the applications of ancient mathematics. I'm going to talk to you a little bit about a selection of topics and projects in Greek engineering and mechanics that I think are interesting. A benefit of mechanics and engineering is that often the evidence comes, as well as in textual format, in an archaeological format, which means there's a bit more solidity to it, but it also means that it requires a different sort of interpretation and thinking. I'm going to start with something from the pre-Socratic period, an archaic aqueduct tunnel on Samos, which is a really fascinating glimpse of the sorts of technologies employed in the period. Then I'll talk a bit more about Archimedes, who came up last week at some length, but this time I'll talk about some of his mechanical inventions, and particularly some of his siege inventions. And then I'll talk about some other Hellenistic inventors, including Ctesibius and Hero of Alexandria. Then I'll move on to the Antikythera mechanism, which is perhaps one of the most famous mechanical or technological devices from antiquity. But to start, let's have a few words from Pappus of Alexandria, who I also discussed last week, and who was a mathematician in the 4th century. So this is from Pappus on the topic of mechanics, and I think it's just quite an interesting little kind of taxonomy of mechanics and technology. So I quote, "The study of mechanics, being useful for many important things in life, is with reason thought by philosophers to be worthy of the highest approval, and is eagerly pursued by all those interested in mathematics. Those mechanicians associated with Hero, so I'll talk about Hero later, say that mechanics has a theoretical and a practical part. The theoretical part consists of geometry, arithmetic, astronomy, and physics. The practical part of metalworking, building, carpentry, painting, and the manual activities connected with them. One who has been brought up in those branches of knowledge from childhood and has acquired skill in those arts and who has a versatile nature will, they say, be the best inventor of mechanical devices and the best master craftsman. But where it's not possible for the same man to excel in so many branches of mathematics and at the same time to learn the arts we've mentioned, they recommend a person who wishes to engage in mechanical work to make use of those particular arts he's mastered. The most necessary of the mechanical arts, from the point of view of the needs of life, are these. 1. The art of the constructors of pulleys, who were called mechanicians by the ancients. With their machines, they use a lesser force to raise great weights against their natural tendency. 2. The art of the makers of instruments necessary for war, for these too are called mechanicians. Missiles of stone, iron, and the like are hurled at a great distance by the catapults that they make. 3. The art of machine makers, properly so called. Waters easily raised from a great depth by the water lifting machines that they construct. 4. The ancients also called the wonder workers mechanicians. Some invented pneumatic devices, such as Hero in his pneumatics. Others seem to imitate the movements of living things by sinews and ropes, as Hero does in his automata and on balances. And others use floating objects, as Archimedes in his work on floating bodies, or water clocks, as Hero in his work on water clocks, which is evidently connected with the study of the sundial. 5. They also called mechanicians those who are skilled in sphere making, who construct a model of the heavens by means of the uniform circular motion of water. So there you see a taxonomy of different subfields of mechanics, different things you can do with mechanics. And you may have noticed that although Pappus does refer to building and painting and things like that, he doesn't strictly include architecture under technology and mechanics here. And it's a subject of some debate, and it's certainly a subject that scholars take different positions on, whether you should include architecture and building under this overall label. So some histories of ancient technology will include material on architecture, others won't. Sometimes that's found in more kind of archaeological literature. In this lecture today, I probably won't talk that much about architecture, although arguably the stuff I'm talking about with aqueducts and so on is a form of architecture. But it's worth bearing in mind that is sometimes included. So some people do include kind of everything really to do with building and construction and technology. So anyway, let's go on now to the pre-Socratic engineering of the Tunnel of Samos. You'll be familiar by this point with the caveat that comes with a lot of discussion of pre-Socratic evidence, which is to say we have much less evidence from the pre-Socratic period than for most other periods. However, when it comes to architecture and engineering, we're in a bit of a better position than for most sciences, simply because of the physical remains. So I have a favourite example of pre-Socratic engineering, which I'm going to talk about first, and that is the Tunnel of Eupalinos on Samos. This was a water tunnel that cut through Mount Castro, and it was used to supply fresh water to Samos even during times of siege. So we have textual evidence from the tunnel from Herodotus, and I quote, "I've dwelt on the Samians for so long because they engineered 3 of the greatest works of all the Greeks. The first of these is a tunnel through a mountain 150 fathoms, so that's about 900 feet high, with a mouth starting at each end. The length of the whole tunnel is 7 stades, that's about 4,200 feet, 8 feet high and 8 feet wide. Through the entirety of its length, there runs a channel 20 cubits, so that's about 30 feet deep, and 3 feet wide, through which the water flowing from a great spring is carried by pipes to the city." End quote. So the tunnel was rediscovered in the 1880s, but it had probably been in use till around 600 AD. The first person to do a kind of full survey of it was a German scholar named Ernst Fabricius, and he noted that right in the centre of the tunnel, beneath the apex of the mountain, there's a strange dogleg, and I'll put that up on your screen now. So what was going on here? Well, this was there despite the fact that the tunnel's perfectly straight elsewhere, so it can't have been just a mistake. So Fabricius he argued that this indicated that the tunnel had been constructed from both ends at once, with the stone cutters meeting in the middle where the dogleg is, which is quite a startling feature when you actually think about what that would involve. Fabricius also mentioned in his report that the main tunnel itself contained a smaller ancillary channel along which the pipes for the spring's water are believed to have run, and I'll put a diagram up on your screen now. So Herodotus corroborates this with his discussion of a separate channel for the pipes. Fabricius's exploration revealed that although along the north section of the tunnel this secondary channel was set into the eastern wall of the main tunnel, by the time it reaches the south section, the secondary channel dips below the surface of the main channel and it ends up entirely separated, running along underneath. The purpose of this secondary conduit is so as to help with the gradient. So digging a constant gradient, a very, very shallow gradient over a long stretch can be quite hard. So instead what they did is dug the tunnel basically flat and had this secondary channel, which was then much easier to construct the gradient of this smaller secondary channel. So this is a very, very clever way around that problem. So this is really a huge project with a very ambitious construction, and it's got this extremely neat execution. It poses quite a few questions, some of which remain still not definitively answered. So the Tunnel of Eupalinos is the second tunnel of its kind we know to have been built by digging from both ends. Most ancient tunnels are of a very different style, which is where you join up a series of boreholes. You sort of bore down into the earth, and then at the bottoms of the boreholes, you join them up. Because digging the tunnel kind of fully from both ends, the level of the earthworks required is quite intense. There's another even more ancient example of tunnelling from both ends, and that's Hezekiah's tunnel in Jerusalem, which is a smaller aqueduct, which bears an inscription with information about its construction. A scholar called Kastenbein, who made the second extensive survey of the Tunnel of Eupalinos in 1960, put forward two suggestions for explaining the tunnel's dogleg, and these were on the basis of the comparison with this other tunnel. So he says one option is maybe this. So sounds are often distorted underground. So maybe the two digging parties might have been unaware or deceived as to one another's position and both dug too far east. The second option, he said, maybe there was a slight error in the calculations and the digging parties believed they should have met already, so they began to look for one another. What seems more likely, as various others have noted since, is that the turn was intentional. This weird little dogleg, they actually maybe meant to do it like that. Eupolinus may have realised that if there was even a minor error in the calculations, the tunnels could miss one another. And in a way, there'd be nothing worse than them starting from both ends and both digging all the way through because they missed each other. So in actual fact, the tunnels were very much on course, and with only a couple of feet of inaccuracy. Most of the inaccuracy was really just in the relative heights, which are about 5 to 6 feet apart, rather than the lateral distance. So they would actually have met if they had carried on. But Eupolinus may have realised that that was a bad idea, and he may have decided that if both digging parties, when in earshot of each other, took a sharp turn to the east, they'd be digging perpendicular to one another and they couldn't possibly miss each other, which, Euclid's parallel postulate comes to mind. I'm sure you don't need to think about it in terms of sort of Euclidean geometry to realise that. But that, for me, is very much the more plausible explanation, and it explains why the tunnel meets at a nearly perfect right angle. So by using the principles of parallel and perpendicular lines, Eupolinus could ensure that the two halves of the tunnel met neatly in the middle. And that's just it's quite a basic example, but it's quite an interesting example of the way in which you might decide, rather than do something in a kind of straightforward, common sense, we dig from both ends, of course we'll meet each other, that you apply a kind of geometrical principle to sort of shore up or to kind of ensure that what you're doing is going to work. I bring this example up because it follows on quite well from last week, from my mentions of geometry and its practical uses. But I think it's also just a really good example of the kind of large-scale engineering works being undertaken at an early date. Both it shows how large-scale some of these works were, but also the kinds of reasons works were undertaken. So we know that the tunnel was financed by the tyrant of Samos at the time, and we know that explicitly part of the reason was as a siege defence, i.e. so that if the town was under siege, the residents would still be able to get water. And discussion of sieges moves us quite neatly on to the next figure I'm going to talk about, who is Archimedes. I talked about Archimedes and his geometry last week. I also mentioned his heuristic and the fact that after the rediscovery of the Archimedes palimpsest, we did get a clearer idea of the ways in which Archimedes might have used mechanical methods to find some of his results before he proved them geometrically. Archimedes was, of course, very well known for his mechanics, not least the discovery about sitting in the bath and the displacement of water. I'll talk first about a few principles of Archimedes' mechanics and engineering, and then I'll talk about some specific inventions, including the Archimedes screw and the Archimedes claw and some other defensive weaponry made for the siege of Syracuse, in which Archimedes lost his life. So let's begin with the law of the lever, which is one of the most fundamental principles of Archimedean mechanics. It's stated in its simplest form like this: magnitudes balance at distances reciprocally proportional to their weights. So there's a diagram of that on your screen now. So it seems quite simple to us, right? And we learn this pretty early on in school, and this idea that, you move something further down the lever, you'll need to balance it out. What's interesting about the way Archimedes does this is that he first works this out for commensurable magnitudes, so putting a thing on each end that is that the magnitudes of the items scale to each other. But then he does it for incommensurable magnitudes, So it's this kind of two-step discussion and proof. One, and this law of the lever is then used in almost everything. And of course, it must have been known in a kind of practical sense prior to Archimedes. But the fact that he's the first one to kind of that we have the text of, he's the first one to kind of discuss it and really go through and explain and prove it. One of the most basic yet most important inventions that Archimedes did is the Archimedes screw, which was used mostly in irrigation systems. It's simply a big screw inside a hollow pipe. I've put a diagram up on your screen now. And when you place that in water and you turn it either by hand, by windmill, or other means, say you could have an animal turning it, it raises water, which goes usually into a trench, which then has pipes funneling the water off for irrigation. Now, it's not clear if Archimedes actually did invent this. It's possible that it was known before, or perhaps it was just unknown. Perhaps it was unknown to the Greeks prior to Hellenistic times, but it had been invented in other places. But Archimedes' name became attached to this invention. And it's a very basic machine, but you can see that in an agrarian economy, anything that improves irrigation, things like that, has the potential to be an enormous transformative innovation. And Archimedes screws are indeed still used today, although, of course, most of our current sort of agrarian or agricultural irrigation is much more complicated these days. Archimedes screws are still used in modern sewage treatment plants, for example. So the one thing that you don't get from Archimedes screw is you don't get an even flow of water over time, but you don't need that in a sewage plant. So they do still use a kind of basic version of the Archimedes screw. Some of the other inventions that we know that Archimedes did, some of the most interesting ones for modern readers, and certainly I found the most interesting, are what's known as his war machines. So during the siege of Syracuse, according to our testimony, Archimedes had various ways of repelling the invaders. And this is so he dies in 212 BC, so this is a bit before 200 BC. So here's an excerpt from the testimony later of Plutarch. Plutarch says, "Beams were suddenly thrown over the ships from the walls, and some of the ships were sent to the bottom by means of weights fixed to the beams and plunging down from above. Others were drawn up by iron claws or crane-like beaks." End quote. Plutarch's writing 400 years later, so this is likely not based on kind of eyewitness accounts, but clearly some of these things have been kind of transmitted over time. So Plutarch goes on, and here it starts. People have always read this as being a bit fanciful, so he starts describing ships being flung around and smashed against the walls. And in a parallel testimony from the even later writer John Tzetzes, there's also a mention of these two types of destruction. That is, A, rocks and other items being dropped on the ships, and B, a claw which somehow lifts or tips the ships. So what are we to make of these references? For a long time, it was thought that these were just kind of later testimonies. They were kind of shaggy dog stories, or they were things that had become massively embellished in the years between the actual siege of Syracuse and Plutarch's writing, and that it just what was going on. I mean, some people did argue that the dropping rocks machine sounded quite plausible. But in general, the view was that the claw that was actually lifting and tipping machines, lifting and tipping ships, just how would you do that? There's a very dumb but quite fun documentary made in 2005 for the Discovery Channel series Super Weapons of the Ancient World, which has a kind of dramatic voiceover and is exactly what you're thinking it's going to be. And it reconstructs both types of the Archimedes war machines and shows how they both might have worked. There's also a BBC documentary series called Secrets of the Ancients, which dedicated an episode to the Archimedes claw. And if you're into this kind of thing, I highly recommend finding them. But I think they're both on YouTube. So here's roughly how it might have worked. I've got a slightly silly diagram up on your screen now. So there's also, and I'll put it up as well, an artistic depiction from the 16th century by someone called Giulia Parigi, and that's just for interest's sake. This clearly captured people's imagination as a type of war machine. So in the two reconstructions of the claw made by these documentaries, it worked something like this. So there was a central wooden tower which supported a rotating boom, perhaps with a counterweight, and that was built behind the city wall, and here's a screenshot from one of those documentaries. From the boom, which may have had kind of supporting straps or struts, either of wood or maybe metal chains. So you've got this boom that's got this counterweight, metal chains or wooden struts, and then from the boom hangs a long metal chain. And in the case of the Syracuse original, it was probably made of bronze. On the end of the long metal chain, you get a weighted, jagged metal claw, that looks sort of like the side of an anchor. So just one side of an anchor. So with enough pulley systems, and we know that Archimedes did make a lot of pulleys, and we know, from that testimony of Pappus, that pulleys were considered to be one of the most important parts of ancient mechanics. So with enough pulley systems, the claw could be released quite quickly from so it could be swung back on the boom and then released quite quickly to smash into the side of a ship. So it would have barbs on it, and given sufficient energy in the swing, it would stick into the side of the ship. The claw would then be slowly raised, and if the barbs held, it would tip the ship with it. If the ship could be tipped far enough, then water would start to rush in and it would sink. Now, this silly diagram of mine shows the ship tipping from the end, but that's actually misleading. I'm afraid I couldn't find a way to use the kind of stock cartoon ship clip art tipping from the side, and I couldn't be bothered to make a whole new graphic for it. Interestingly, Giulia Parigi's painting, and in fact most other artistic depictions of this, also show the claw tipping ships from the end, usually from the stern. But that's not what they did when they did the reconstructions in the documentary, and as you'll have gathered from how I just described it, the claw was going into the side of the ship. And if you think about the law of the lever, which I've just talked about, which Archimedes formulated, you may be realising that in terms of force, tipping from the end is actually totally not the most effective way. If you think about the distance you need to pull the stern up in order to flood the ship. Instead, if you pull from the side, you require significantly less force in order to essentially roll the ship enough that it might start to sink. So if the claw was being used in combination with the rock dropper machine, which would be a similar sort of thing with a boom that moves across and just some kind of release mechanism for dropping stuff, so that's much simpler to construct. If you were using these two things together, you can imagine how it could have sunk quite a lot of Roman ships, provided they came close enough to the city walls in order for the claw to be able to even grab them in the first place. So maybe Plutarch's description of ships being kind of fully thrown around is a bit fanciful, but there's no reason to doubt that Archimedes could have sunk ships using this. And given his knowledge of the law of the lever, he would certainly have known the most kind of force efficient way to do it. But what about if ships were further away and didn't come in close to the city walls? You can imagine this kind of thing would work for a while, but then the Roman captains would get wise to it, and they would not bring their ships close enough to the city walls, and might try and barricade in some other way. Well, we have another attested invention of Archimedes, another siege machine. And this time it's of quite a different type. It's the use of polished bronze sheets as mirrors. So here's what John Tzetzes has to say. He says, I quote, "When Marcellus, the Roman commander, withdrew the ships to a bow shot in distance, the old man constructed a kind of hexagonal mirror, and at an interval proportionate to the size of the mirror, he set similar small mirrors with 4 edges, moved by links and by form of hinge, and made it the centre of the sun's beams. its noontide beam. Afterwards, when the beams were reflected in the mirror, a fearful kindling of fire was raised in the ships, and at the distance of a bowshot, he turned them to ashes. End quote. This story is a bit more apocryphal. It's found at its earliest in Lucian and Galen, both in the 2nd century AD. So again, it's some hundreds of years after the siege actually happened. Tends to be suspected a bit more. But actually, it is easy to see how this could be done, and the use of mirrors to start fires is certainly possible. And I think from the description, the use of the kind of secondary mirrors around the outside that kind of focus the beam even more make it, to me at least, relatively plausible. The other two major named inventors we know from Greek history are Ctesibius and Hero, both from Alexandria in Egypt. Ctesibius lived in the 3rd century BC, and Hero about 200 years later in the early 1st century AD. The two inventions are usually attributed to Ctesibius are the hydraulis, a type of water organ, and a vastly improved version of the clepsydra, the water clock. I'll talk you quickly through how the clepsydra worked. So very early clepsydrae, and they were used right from archaic times, were basically jars with holes in, and when water ran out, the time ran out. So really they were more like stopwatches than clocks. And I've got an example up on your screen now, and this is two clepsydrae that run into each other. However, this kind of basic form of the clepsydra doesn't work very well, because the amount of water in the vessel decreases, the water runs more slowly. So the amount of water doesn't scale linearly with time, and you can only, therefore, you have to know what the different quantities are for the different measurements of time. So it's very useful for things like timing court speeches, and we know that was one of the things they were used for a lot. But it's not very good for kind of actually keeping time in any sense. And we know that even from the archaic period onwards, there were clearly some attempts made to counter this problem of flow and to linearly scale the timing. The shape of the vessel and the shape of the spout can help a lot with this problem. And so clepsydrae were shaped in such a way as to kind of counter this problem of the flow decreasing. However, as good as you can get this, the clock still can't run continuously. So to keep the clock running and have it be really a clock rather than a stopwatch, you need to find some way to top the jar up. And this is Ctesibius's construction. So it had a higher supply vessel and then a measuring vessel beneath. And he also worked on the problem that the spouts could wear out over time. This was a problem that if your spout wore out, then the time of the clock would be different. So really not what you want. So one problem was that spouts of softer materials could be worn down over time. So pottery, the flow of water over the course of a couple of years could really degrade the spout such that the hole would be bigger and therefore the water would run faster. So your clock would run too fast. Or another option was if you're living somewhere with hard water, mineral deposits could gather in the spout, which would reduce the size of the spout, and that would slow down the flow, and so your clock would run too slowly. And you can see that in lots of contexts, if you're timing something quite roughly, and remember you're living in a world prior to accurate timekeeping, so it's not like everything's running on kind of perfect time and you always have to be on time for things, and there's much more flexibility in when things happen and so on. Nevertheless, you can see that there's settings in which this would be really problematic, and the one that's always given is the case of law courts, where you want to ensure that speakers from each side of a case have the same amount of time. And you can see how having a kind, the accusation of, the court's clock is, the spouts run out, and so actually so and so is getting more time on his clepsydra than I am on mine. So you can see why people would want to kind of make sure that this was accurate. So Ctesibius diagnosed two options. One of them was to make, in the case of hard water, to make the spout from gold. Gold is quite resistant to deposits settling on it, and so that would keep it flowing regularly. Or, in the case of the degradation of the spout, to use jet or gem. And you can see that these are clearly quite expensive options, but they would keep your clock running smoothly. The other innovation that Ctesibius made was to make a dial for the clock. And here's a 19th century illustration of what that might have looked like. So the person on the pole there is the hour indicator, and that ascends, that floats as water flows in. But then there's also a bit at the bottom with a water wheel and a series of gears that rotate a cylinder to show the hours. So Ctesibius found these ways to make these clocks really quite sophisticated. And you see this water clock engineering becomes quite a big thing in the medieval Islamic world. So as well as inventing things that we might consider useful, or they indeed might also consider useful, although that distinction is maybe one worth thinking about, whether our ideas about what's useful are the same as Greek ideas about what's useful. Anyway, as well as inventing things that clearly had a kind of really functional purpose, like a water clock, Ctesibius and Hero also made items that were designed to kind of induce wonder or be kind of marvels rather than having a strictly practical use. So Hero of Alexandria invented a device called the Heliopile, which in histories which talk about Hero, frustratingly, this is quite often referred to as the first steam engine, but actually it's not really a steam engine at all. It is a steam powered device, and it's the first one we know of from antiquity. So the way it works, and here is another much later drawing. So it's a spherical vessel. It's got these curved nozzles that come out of the vessel, and it's really important that they're curved and that they're opposite to each other. So the vessel is pressurised with steam, and then that steam escapes out of the nozzles, and because of the curvature of the nozzles and their direction, it spins the vessel around. So you can either have it, there's two ways you can do it. You can either have a boiler underneath the sphere, but then you have to have a kind of complicated system that allows the sphere to rotate. More simply, the sphere itself is the boiler, and so it doesn't have to be a sphere, it could be a cylinder, but that's the more simple version. It was probably used as a novelty object. There's no indication from antiquity that this was ever seen as something that could be kind of used to revolutionise mechanical processes or agricultural processes or drive chariots or any of the things that we think of when we think, wow, they invented the steam engine, why didn't they then immediately have the kind of industrial revolution? Well, clearly their ideas of what the purpose of this was or what its uses could be or even why you'd make something like this were very different, and there are various reasons that might be. I mean, one thing is these things must have been very expensive to construct, and perhaps they were just like, why would you do that? Why would you make this when there's a plentiful supply of labour in the form of, in particular in the Greek world, of slavery? And you can think maybe in a world in which labour was in plentiful supply and materials were expensive, it wouldn't have made sense for them to try and construct loads of these. They weren't actively seeking labour-saving devices. Or maybe they just, maybe Hero's project of engineering was, he was so used to making novelty objects or objects for use in temples, that's the thing that I'll come on to in a minute, that he was seeing things entirely in that kind of realm, and it would just never even have occurred to him to use it in some other way. But it's a question that's kind of always asked with this object, and the Heliopile is one of those things that it crops up in documentaries about ancient technology, but it's almost always referred to as the kind of first steam engine. And the question you should always ask with these things when people say, like, oh, it's the first steam engine, oh, it's the first it's the first mechanical clock or whatever. We'll get on to that with the Antikythera mechanism. Is, well, where were the next ones? Why have we actually got the evidence that this sparked off a kind of new way of doing things, or should we be seeing it in a different way? The Euclid temple. So both Hero and Ctesibius made, and I'm sure there were others whose names don't come down to us, but who made objects that were used in temples as part of a wider set of marvels. So we know of other things like counterweighted doors, which were appeared to be sort of automatic doors that opened at the right moment to show you probably they would open in to show you the statue of a god. And that must have been great. I mean, that must have been a really kind of marvellous occurrence of the doors opening right at the right time in a ceremony. They even had things like sort of vending machines where you put in a coin or a token and you get incense or something like that. And those were also for use in temples. And you can kind of see why temples would want to have these marvellous inventions that really enhanced the experience of going to the temple, and that were about paying respects to the gods. There were also some automata, we know, made in antiquity. So the eccentric tyrant of Athens, Demetrius of Phaleron, so he was around in the late 4th century BC, is said by Polybius to have commissioned a huge moving replica of a giant land snail, which led the ceremonial procession of the Dionysia, travelling nearly 2 miles through the city. There's quite a good book on robots in antiquity by Adrienne Mayer, and she's explained that the snail had a kind of particular joke value. It was deliberately very slow, and then it was followed by donkeys in the procession to be kind of maximally ridiculous. Alfred Rehm in 1937 proposed, also talking about the snail, proposed that the way this worked was that it had a treadmill with a man on it inside the snail, so it wasn't really an automata. Maybe that's the case. We know treadmills did exist in antiquity. It's certainly weird and entertaining. And while we're on the topic, a little known detail, this time not from Greece, but from Rome, is that for Caesar's funeral, Mark Antony commissioned a mechanically rotating wax effigy of Caesar, which was complete with stab wounds, which I find very funny, although perhaps I shouldn't. In the year 1900, a group of Greek sponge divers found, near the tiny island of Antikythera, a shipwreck about 60 metres down on the seabed. Very little of the timbers of the ship were left, but there were many artefacts, including a huge collection of bronze and marble statues, various amphorae and other pottery, glassware, and nestled unobtrusively in this huge hoard was a strange calcified metal contraption with fragments of a wooden box still clinging onto it. This was what's come to be known as the Antikythera mechanism. The full story of the Antikythera mechanism, if you don't know it, is certainly worth following up. It's a real tale full of twists and turns, and it's brilliantly and accessibly told by Joe Marchant in a 2009 book that I'll put on the bibliography at the end. I'll show some images of the mechanism as I speak about it, and I'll talk a bit generally about it, and then in a minute I'll explain a bit more about how it actually worked. But in short, by the 60s or so, scholars were fairly sure of the date of the Antikythera shipwreck by a mixture of carbon dating and comparative dating of pottery and other everyday objects found in the shipwreck. They could date it pretty precisely to the 1st century BC. This was helped by the additional discovery in the 1970s of coins minted between 76 and 67 BC, which implies that the ship sank sometime in the 60s BC, likely en route to Rome. The purpose of the mechanism itself was also a battleground for various scholars. Early suggestions, including that of Ioannis Phoronos in 1903, were that it was some particularly complicated form of navigational astrolabe. Others argued that its resemblance to clockwork, the presence of interlocking geared wheels, which you could just kind of see in the calcified ruins, meant that it was more likely to be some kind of mechanical clock. The first major scholarly work done on the mechanism was by Derek de Solla Price, who argued that it was a calendrical planetarium, i.e. it displayed the planets and the heavens. We have a reference to it, or to something very like it, from antiquity. Cicero, in fact, mentions an object that sounds very much like the Antikythera mechanism, and this comes from his De Re Publica. So I quote, "I had often heard this celestial globe or sphere mentioned on account of the great fame of Archimedes." So the implication there is that Archimedes made this. I'll come back to that point. So going on, Cicero says, "Its appearance, however, did not seem to me particularly striking. There is another, more elegant in form, and more generally known, moulded by the same Archimedes, and deposited by the same Marcellus, in the Temple of Virtue at Rome. But as soon as Gallus had begun to explain, by his sublime science, the composition of this machine, I felt that the Sicilian geometrician must have possessed a genius superior to anything we usually conceive to belong to our nature. Gallus assured us that the solid and compact globe was a very ancient invention, and that the first model of it had been presented by Thales of Miletus, that afterwards Eudoxus of Cnidus, a disciple of Plato, had traced on its surface the stars that appear in the sky. He added that the figure of the sphere, which displayed the motions of the sun and moon, and the 5 planets, or wandering stars, could not be represented by the primitive solid globe, and that this, the invention of Archimedes, was admirable because he'd calculated how a single revolution should maintain unequal and diversified progressions in dissimilar motions. When Gallus moved this globe, it showed the relationship of the moon with the sun, and there were exactly the same number of turns on the bronze device as the number of days in the real globe of the sky." So we think what he's saying there is, although you might think it would be more impressive to have an actual spherical globe model, like a kind of armillary sphere or an orrery, he was initially unimpressed because this is a flat device. It's got a panel on the front which is flat. He then comes to realise how brilliant this is because you turn just one handle and all of the different motions are represented. So more recent work on the Antikythera mechanism has focused on how that could be possible, how that mechanism might have worked.
The first model of it was by a guy called Michael Wright.
And in a minute I'll show you a video of a model of it. 2 of the main scholars who've worked on the mechanism in recent years have been Alexander Jones and Tony Freeth. In fact, Tony Freeth and a team from UCL published a paper just last week, which reconstructs the gearing more accurately than has been previously possible. So, how did it work? It's agreed that the Antikythera mechanism was a rectangular box which had 2 displays, one on the front and one on the back, both driven by the gears inside the machine. On one side, the display showed the periods of the planets. On the other side at the back, it had a much simpler design. It had a month calendar with events marked in and an eclipse calculator. How the system of gears worked and what the displays look like is the area that's contested. Michael Wright's model, and most models since, use pointers like the hands of a clock to represent the periods of the planets. So here's a short clip of what that looks like. By contrast, the new model from Freeth et al. Suggests that the planets were represented by jewels on rotating metal rings. But how did the gearing work inside? As I mentioned, on one side the display showed the periods of the planets. So what does that mean? That's the apparent cycles of the planets' motions against the backdrop of the fixed stars, including their retrograde motion. And I discussed how that worked in some detail in the 3rd lecture. So you can represent these periods numerically by how many cycles each planet goes through in a given number of years. And these estimations have been known since Babylonian astronomy, but more and more complex estimations can be given. So a decent estimation, or a sort of basic estimation for Venus, is that it goes through 5 cycles in 8 years, and that can be written as such, 5, 8. But that's only an estimation, so it doesn't fit exactly. And if you use larger numbers, you can usually get more accurate estimations. For example, for Venus, a more accurate estimation known to the Babylonian and Greek astronomers is that it goes through 720 cycles in 1151 years. But that's really hard when you think about how to do this mechanically with gears. It's all very well in a kind of purely mathematical model, but when you're trying to actually physically model this, you can't make a gear with 1151 teeth. That's just too mad. And because it's a prime number, you also can't factorize it, so you can't do anything with it. 5 cycles in 8 years, well, that would be quite easy to make with gears, but it's not really very accurate, and if you want something a bit more accurate, you're going to have to do something else. And what's worse in all of this is that this ratio is different for each planet, meaning each planet requires a different set of gears to represent its motion, because you're trying to get them all on one big dial. So what's cool about this new paper is that it uses some discoveries made by CT scanning of the mechanism that was done in 2016. And yes, I do mean CT scanning as in the medical imaging technique. They used a CT scanner called Blade Runner to make some images. And they found, so there's quite extensive inscriptions on the panels of the Antikythera mechanism for what remains, but it's been very, very hard to read because it was the bottom of the sea and it's all sort of calcified. But they found in one of the extensive inscriptions, in a bit where it's talking about Venus, the number 462. And they realised that this is an estimate of a period for Venus of 289 cycles in 462 years. So Freeth and et al. Point out that while you can't make a gear with 462 teeth, it's just too hard, you can factorise it into smaller numbers. And the great thing about gears is that you can use the combination of 2 or more gears to get the number you want. So once you can work out some of these better approximations of the periods of the planets, you can start factorising them to find the number of teeth for the constituent gears, which you can combine to make the right motions. In particular, if it's possible to use shared gears between different planets, well, that's advantageous because the aim you've got here in making the Antikythera mechanism is to represent all of the planets, so that's Moon, Mercury, Venus, Sun, Mars, Jupiter and Saturn, as well as the eclipse thing, but I won't go into that. So you're representing a lot of different things in the most kind of economical or parsimonious way possible. You've only got a certain amount of space. You don't want to kind of use up tons and tons of gears. So what you're trying to do is use the fewest number of gears to represent all of those motions. But obviously you have to construct it in the right way so that they all move in the right way. So you can see that it's really complicated, but that you can indeed, if you can find overlaps, use the same gear for 2 planets. As a constituent for 2 planets. So, for example, Freeth et al. Conjecture that one of the gears must have had 17 teeth. And that's an unusual number when you're thinking, if you're thinking about a normal geared machine as we think of them now, a kind of regular mechanical process of even time and so on, you never use a gear with 17 teeth. It's just too silly. But it makes a lot of sense if you're thinking about it when it comes to something like this, when you have to use exactly the right combinations and you need to use exactly the kind of common factors with other planets. So you get these gears with these really weird number of teeth to reach a precise number. And so we know for certain that there was a gear with 63 teeth, and that's survived well enough to have been counted. And that's a constituent for one of these planets. In the case of the 17-toothed gear, Freeth et al. Explained that it could be used both for Venus and for Saturn, so it would be a common factor of the best approximation for both of them. And that sort of arrangement you can conjecture, as Freeth et al. Go on to do, for all of the other planets as well. And it's an incredibly complicated piece of mathematics, but they've done it. And in this way, you can design a version where all of the gears have fewer than 100 teeth, and all of them are connected to the main drive wheel, which is driven by a little handle outside the box. And that's what we think Cicero was referring to in his description. So I hope that's given you just a little bit of a picture of how this worked, and you can see how massively and intensely complicated this was. And one question that gets asked about the Antikythera mechanism is, well, what was it for? Was it meant to be a kind of accurate planetarium that you could make predictions with? I think the answer to that is probably not. Planetary predictions were made using, without a kind of mechanical object. They were made from sort of, well, earlier than Ptolemy, really, mathematically. And you can do that with these complicated ratios without having to go through the incredible headache of trying to make it all into gears. I think much more likely was that it was, as well as being a sort of scientific object, it was an aesthetic object, it was a display object, would have been the Freeth et al. Say that the planets were probably represented by precious stones. It would have been owned by somebody extremely rich, would have been owned by somebody extremely cultured who wanted to show off how extremely cultured they were. And one of the recurring features of Greek and Roman philosophy is this idea that knowing about the natural world, knowing about the heavens, having sort of a philosophical display of knowledge was part of being part of the kind of cultural elite. And I think it's much more easy to imagine the Antikythera mechanism in that way, which is why it gets into the work of someone like Cicero. Do we think Cicero would have understood the exact mechanics of the gearing? Probably not, but he could nevertheless understand the kind of wonder created by an object like this. I'm not going to make any extensive concluding remarks, but I hope this lecture, and indeed this whole lecture series, has given you a bit of a window into some of the cool and interesting scientific topics that ancient Greek writers thought and wrote about. I think if there's one takeaway, it's the enormous variety of Greek scientific thinking, but also to be... That as a historian of science, I think it helps to be somewhat relaxed in your thinking about disciplinary boundaries, about what really counts as science, what really counts as philosophy, what really counts as religious thinking, and so on. These things this is a very different world to our world, and sometimes it pays great dividends to kind of happily go over those disciplinary boundaries and try and see the ancient writers and ancient thinkers on their own terms. But I hope you've enjoyed this lecture course, and that it's made you want to go and read some more about ancient Greek science.